Okay, so this short video is to continue our discussion on current mirrors, right? And you were given a homework, if you remember. We were talking about the cascode, the benefit of cascode, right? So basically, it's the resistance which you have from here, R naught, which increases, right? Because there is a factor multiplied by G and RO in the resistance. So that's why you get the effect. So how does that directly affect when you increase RO? By default, the effect of lambda is reduced, right? Because we know that R naught is nothing, is just lambda ID, right? So that means that whenever there is an effect or effort to increase RO, you would have lesser effect of channel length modulation, right? And that is, we saw that by doing so, we can minimize the error which would come in copying this IREF to I out, right? So, but the problem here was that there is a bias voltage which we needed for this cascode transistor. So how do we bias it? For that, we saw that we could again have another transistor in series, right? So this MO, which comes to give the same gate voltage. So you convert your I to V, right? So there is a VB here, which you are getting, and then there is a VB. So let's say VB1, and this is VB2, which you are generating, right? Using this. So now, if we see what is happening, if you were to write, because the question which we were having was, this is good that if you can minimize the error, but what is the downside of this architecture, right? And clearly, when somebody looks at multiple transistors on top of each other, you see the headroom which you are getting, right? Or the swing, which we will talk about also in amplifier, is quite mm, uh, so it's quite reduced. And the reason being, because you see that these two transistors, when they put on top of each other, we would need at least some voltage across this transistor, right? Which is VOV. VOV is your overdrive voltage, which is needed for these transistors to be in saturation, right? So that is the condition. So that VDS3 min which we need is at least VOV. And similarly for here also, we see that VDS min of your 2 is also VOV, right? Now this is, so let's call it, this is VOV1 and this is 3 and 2 is more apt, right? Based on this thing. So then this is 3 is your VOV3 and this is 2, right? So now let's find out what are the values of these VOV2 and VOV3, right? What is the minimum value we need to have? And what is the why VOV different is because the gate voltage depends on VOV, depends on your VGS, right? So it's VGS2 minus VT of this transistor. While your VOV3 is nothing, it's just again VGS 3 minus VT, right? So VT is same for both the transistors. And we see that VGS3 is obviously, if we were to expand it, we can write. So S2 is 0. So it's basically nothing, is just VG2 minus VT. But for VOV3, we see it is VG here minus, or sorry, VG3 minus VS3. VS3 is nothing, is VY. So there is a different voltage, right? Vy minus Vt, right? So, and Vy is basically VOV2, right? Which is what we will see. So now, if we start from here, let's say, let's first find out what is VG2 value. So when we see there is a IREF passing through this and there is a IREF passing through, so the value of Vx, right, which is basically Vx minus Vt, the value of Vx is nothing. What is the value of this, right? So you would know, if I were to write in the terms of VOV, this would be VOV, so which is 2, let's say VOV2 plus VT, right? We can calculate from here, right? We are writing everything in terms of VOV, let's say. So VOV2 plus Vt is the value of Vx, right? Which is this value. Now, if I want this transistor also to be in saturation, sorry, it's already in saturation, but the value of this transistor, because the same way we can write now, because we are writing the value of Vg, right? This value, VB1. So VB1 would be this minus, this is your VGS, right? And this is minus Vt is your VOV, whatever is the VOV of this transistor, right? So then we could write this in terms of that the VB1 is your Vx plus Vt plus VOV. Okay. So if this was VOV or VOV2, but the VOV is the same, right? You see here that it is written in terms of VOV. So that means now if we were to see this, you clearly see that you get the value here you get is 2, because if we put the Vx value, this would be, so what I'm taking here is VOT is VOV, right? Because it's the same transistor. So then your, because the current is same, right, in both the transistors, so VOV is same and the WL is same. So that means this comes out to be 2 VOV plus 2 VT. So that is the your VOV1. So this node voltage is, you can write as 2 VOV plus 2 VT. This node voltage is VOV plus VT, right? Because it's VGS, and here we see that because there is a VG upgrade, right? So because the VGS has changed, it's not ground anymore, so this is higher. Now, if we were to see the Y voltage, so what would be the Y voltage? We already know that the Vy is just, what is Vy? Vy is just minus of that, right? So that is the voltage Vg3. Vg3 is already 2 VOV plus Vt, 2 Vt, and 2 VOV plus Vt, and then you will have minus Vt from here, and 1 minus VOV, right? So this would be then VOV plus Vt. So you see that though it is V, so though it is the VOV which you are having in this case, but you would need a, you would, so minimum what you need is VOV. But for this transistor to operate in saturation region, you need at this node, whatever Vy you are getting is VOV plus Vt. That is the voltage you need, because here the minimum you can have is a VOV, right? So then this node, what would be the voltage now? Because this is VOV. So basically at this node, then we will have 2 VOV plus Vt. So what you see is that the minimum voltage now I need is, though from here I could see that the minimum I would have needed is VOV plus VOV, right? This is the 2 VOV. But because of what is happening here, that this node VGS of this transistor is needed to be at least VOV, right? So that's the reason why you see that your this node has to be VOV plus VT, and because of that you get a head minimum voltage at P which is needed as VOV plus VT, and that's where you see a problem, because VOV is, let's say, around whatever typically the VOV value is around 0.15 to 0.2, which you will see that you would put or you will use. So, but the problem is the VT, right? Because VT is unnecessarily increasing the minimum voltage needed at that point, which could be much lesser, or at least VOV, right? That is the main thing. So that is the thing, and you can evaluate on yourself, and there are multiple ways to do that, right? There is a, so I have written here in very long form, but you could easily start with the uh, thing that, okay, for each transistor, I need at least VOV here. So if you say the VDS is VOV, then this part has to be more than, so this VG is by default VOV plus VT if you S is 0. Similarly, here we see there is an addition always happens with respect to source of VOV plus VT. That is why you see the transistor here is 2 VOV plus VT. And when you come to S, a VOV plus VT is decreased, right? So that is the, always you see the S is lesser than VOV plus VT. And this you can see from the equations that why it is so. And then when it is VOV plus VT and VOV you are adding here, so then this transistor will be 2 VOV plus VT. Now, to mitigate this, what do we do, right? That is the question. So clearly you see that this transistor is the reason why you are getting this 2 VOV plus VT, right, at this node. Though it could have been just if it was only VOV plus VT, then this would be much easier. Or it would be, sorry, the minimum it would be 2 VOV plus VT, right? That is what we want. So if I draw it again, this is your M2, this is your M3, right? Is it correct? Yeah, okay. This is the current which is flowing I out here. And now what we are saying, okay, this is okay. This we have already tied up to the diode connected, right? And we already have the minimum voltage here, which is VOV plus VT. Now, the question which we were saying that because we have to remove extra VT, so the maximum voltage which I can bear here is 2 VOV plus VT, not 2 VT, right? Because here we were having 2 VT. Because if it is 2 VOV plus VT, then the voltage here would be VOV, whatever I need minimum. So then it is VOV, then VOV plus VOV. So the minimum voltage then I will have here is 2 VOV. Great, right? Because then I removed the VT. So that is what I need. But if I put it in a diode connected format here, then the voltage which you will have here is 2 VOV plus VT. So how do I, sorry, 2 VOV plus 2 VT. So how do I get that voltage is the question now, right? So let's have this first, because we know that this would not be connected like this. So we cannot have another diode connect because that is not going to work. So that means we have to generate this voltage separately, right? And now the question is, how do we generate this voltage separately? So one thing is clear that I cannot have two diode connected generating this voltage. That is not going to work. So that means because I have this I ref, this is just copies available, is there's a possibility to use this IREF to generate this voltage. And this is not in the same branch, right? So I would use a separate branch. And the only thing which I know is that I use something like this. Something like this. All right. If I do this, then you know that the voltage which you get here is VOV plus VT. But what I need is 2 VOV, right? Because if I use all the transistors are, the W by L is same, right? For all the transistors. That is why the VOV you see in all the transistors are same. But now what is the case here is I need, rather than a VOV, I need 2 VOV. And the current is same because current I'm copying, right? IREF I'm copying. Is there a way that I can get a factor of 2 here? That is the point which we have to think of. Is there a possibility that I can get a factor of 2? And once, I think that is something which you can already think. You can say that, okay, this voltage which is generated obviously depends on the current. But does it depend something else than the current? And then I see, yes, because my I, if I were to write I ref, which is some beta or Kn, whatever the factor is, into your W by L and into your VOV. Let's say this is M1, let's call it M4. So this VO4 minus VT square, right? And this is 4. And what I need this to be equal to, obviously, this I out, whatever is flowing here, but I need this, sorry, this is not VOV plus VT, this is just VOV4 square, right? So I know that the current is basically same, right? So the same thing which is flowing in KW by L, which is, let's say, 3, and VOV is just VOV here, right? Because we know that all the W by L is same. So for VOV1, VOV2, and VOV3, they are going to be equal, right? Because your W by L is same in all the cases. So then in that case, what do you see? You see that here, if what do I want to have? I want to have my VO4 to be twice of this VOV, right? That is what I want. If I want this at twice, then this would become KW by L4 into 4 times of VOV square, right? And but I want these two current to be same. So then the only choice I have is that my W by L4, 4 times of W by L4 becomes equal to W by L3. This means your W by L4 would be equal to 1 by 4 of W by L of 3. So if I design this transistor to be 1 by 4th of W by L of other transistors, then I can achieve my VOV or the voltage at this node to be 2 VOV plus VT. And then everything is, we have seen, right, solved. So this is the beauty about playing with the W by L to actually change the bias voltages which you are generating, or VOVs which you are generating on these. Okay, so practice it, do practice on your own this thing, and then you will get it, right? The basic concept what we are having is, what is the minimum voltage I need to have at this point P to keep all the transistor in saturation. And one thing which we saw clearly is that the voltage at the gate node, which I need to, if I were to write in terms of VOV, we write VGS is basically VOV plus VT, right? Because this is the minimum you need to have for this to be saturation. And that is how you see everywhere we are working towards that VOV is less than VT, right? Make sense? Okay.